Alright.
What's the markers not used for Recording Studio?
Sorry?
Do I just click never mind?
Oh yeah, it's okay. Okay. Alright, so what I want to do today is introduce you to how to use Mathematica to solve linear programming problems. I want to introduce you to using Mathematica to solve linear programming problems. That was just to see who was awake. Alright, the screen did turn off for a moment. Mathematica is a very easy language to use once you've used it for many years. The syntax might be a little strange if you haven't seen it before. The more programming languages you know, the more programming languages, more programming environments you've worked in, the more frustrating it is to move from one to the other because the syntaxes are slightly different. And it's always, how do I do this command in this one rather than that one? What I frequently do when I'm in Mathematica is I might open up another window over here just so I can test some codes over here and just see how things are. And how do I do a binomial? Okay, various things. If you want a command and look something up, if I do question mark, oh, bio, it starts doing tab fills, information not found, you can click over here, start doing lots of different searches. Alright. I'm going to concentrate today, I'm going to assume you've already watched the Mathematica video, if not it's online. It's a brief introduction on how to use Mathematica. I want to show you how to use it for linear programming. One of the big things we saw in the previous lectures was using these CSV files. Why did you want something in a file like Excel or something like that? Because if you're doing a linear programming problem that's worth doing, typically you're going to have a large data set or a large number of constraints. And you need some way to quickly generate those matrices, quickly generate all of those conditions, all of those values, and input that into your system. The more you know about Excel, Mathematica, R, Python, any of these environments, the more you can write little script programs or subroutines to manipulate your data and make it nice. And so what I want to do is I want to show you how to solve two problems that we've done before using these methods. And then if time permits, we'll talk a little bit about how to solve the Sudoku in Python or R. So the first is, I just did a question mark linear programming, and this just loads up a bunch of things from Mathematica that start off with linear programming. If I click on the double arrow over there, it gives me a little bit more information. You can click on these and get even more information. Oh, okay, the more information for this one is just further down. And so here are some examples. The main thing to notice, and it says so over here, linear programming CMB finds a vector x that minimizes the quantity c subject, c dot x. So c dot x is the same as c transpose x. It's the dot product of our constraint vector, of our cost vector and our variable vector, subject to the constraints that m dot x is greater than or equal to b. So that's our matrix A is greater than or equal to b, and x is greater than or equal to 0. Is this the same as the canonical linear programming problem? No. What's different from this? And I mean more than just calling it m and not a.
It's not. It's greater than.
It's greater than or equal to and not equal to. So Mathematica has things set up differently than the canonical linear programming problem. If you want equalities, how can you get equalities?
There's 2 rows per equality?
2 rows per equality. Have one row with all, and then the next row you change every sign to its opposite. Multiply through by -1, both on the matrix side and on the vector B side. Because when you multiply through by -1, you flip a greater than or equal to a less than or equal to. So if you ever want an equality, you just have to insert 2 rows that are essentially the same. One is the negative of the other. And it has x is greater than or equal to 0. One thing that I found annoying is I did not find anything here that does binary integer programming. And so in a lot of the problems we want to do binary integer programming. I could not see how to make Mathematica do that. I assume R and Python, they have switches that say, do this in binary. Mathematica has integer programming. Is it a big deal that Mathematica can't do binary but can only do integer? No, what do I do?
The integers 1 and 0.
So how do I do that? So how do I restrict it to just doing, yes?
Oh, it was already.
Yeah.
Sorry. You can just not assign any non-zero, non-1 values to any of your variables.
But it declares my variables to be integers, and it allows my variables to be integers. So how can I restrict my variables so that they're only 0, 1? Mathematica doesn't have that as a default.
Constraints?
Constraints. Add the constraint, each variable is less than or equal to 1. If it's now integer valued and it's less than or equal to 1 and it's greater than or equal to 0, you now have 0, 1 variables. So it's not a huge deal to create a binary integer programming problem in Mathematica. You just have to add more constraints. If you are doing this by hand, if you are typing the matrix by hand, this is not pleasant. Okay? And what you need to do is you need to be able to write small routines to add zeros, or add rows, or whatever like that. The problem I give you on the exam is not going to be at this level of complication. If you can do this, you are more than fine. So the first one is the diet problem. I want 10x plus 4y to be greater than or equal to 9, 5x plus 8y greater than or equal to 11, 3x plus 2y greater than or equal to 5, and I want to minimize 2x plus 3y. So this is clearly my cost, and I have 3 different nutrients and I must get certain amounts. How many products do I have? 2 products, 3 nutrients. And I need to make sure that I get a certain amount of each nutrient or I die. Okay? Alright, so in Mathematica, the way you do comments is parentheses star to start, star parentheses to finish, everything in between. Here's how we do a simple linear programming problem with real variables and sizes are small. We first enter the matrix A, which we're going to enter row by row. We then enter the B vector. We then enter the cost vector. And then the way the code works is we solve ax greater than or equal to b, x greater than or equal to 0, and take the minimum of c dot x. So the period here is the dot product of the 2 vectors. Because the matrix A is so small, it is not worth it to write code to append the rows of A line by line. I have 3 rows of A to add, just add them. And so the braces on the front and the end mean start and end of my matrix, and then this is the first row of my matrix, the second row of my matrix, the third row of my matrix. B, this is the first row, is just a 9, then 11, then a 5. It's a column vector with 3 components. Here's my C. And then solution is linear programming CAB. Whenever you put a semicolon after something, it suppresses the output in Mathematica. So this will solve the linear programming problem, and it will store it in solution. If I now want to call that in, I can now just use the word solution. So I'm going to print the solution is solution. I'm going to print what the cost is. Now let's do it where we require integer values. And so to get integer values, I do automatic integers, and it's going to restrict everything to be integer valued. There will be positive integer there will be non-negative integer valued. There is no regurgitation in the diet problem. You're not allowed to consume negative amounts of something, but you are allowed to consume 0. And so when we solve it, we run the code right now, we get the solution is 9/7, 4/7, the cost is 30/7. Now let's do where we require integer values. Mathematica gives us a warning. It says, integer linear programming will use machine precision approximation of the inputs. The solution in integers is 1, 1, the integer cost is 5. What can you tell me about the integer cost versus the real cost? Slightly higher. If you didn't know exactly what 30/7 was, instead of saying slightly higher, you would say it's not lower. Right? The integer cost is not going to be less than the best real cost. And that's all you need to do to solve something like the diet problem. The code is not that bad. The chess problem is a little bit more involved. And so the chess problem took a little bit of time to code it all in. And so I want to just go through a little bit quickly. So I set up the chess program not just as a standalone, but as a function. So I can call a function with 2 variables. The variables are going to be the board size and the number of queens. So I'm calling my program pawn queen problem. Hopefully this is a good descriptive name. My input variables are board size and number of queens, and print linear programming conditions. So print linear programming conditions is 1, I'm going to have it print the entire output. And the entire output is not going to be just where the pawns and queens are, I'm always going to have it print that. This is going to be printing the constraint matrix. This is going to be printing the vector B and the vector C. So if I'm doing a lot of debugging work, I might want to be printing this stuff out and see what's going on. But when I'm actually running the program at large values, I really don't want to be having all this output coming to the screen. So I don't want to write board size and number of queens all the time, so I'm going to let n be board size and num queens be number of queens. And then we have a little bit of a difficulty in terms of how we do the variables. The way everything is, when you think about linear programming, you have a matrix and then you have a vector. When you think about what's going on, when you think about all the different problems we've done, we often love to have subscripts on our variables. We love to have things like xijt, right? Maybe we're hopping from square I to square j at time t, something like that. Or we're showing movie I on screen j at time t. We love to have indices. We can't do that here. We have to have our variables x1, x2, x3, x4. So what we have to do here is, I want two types of variables. I want xij to be 1 if a queen is at ij, and 0 if there's no queen at ij. And I want pij to be 1 if a pawn is at ij, and 0 otherwise. So what we're going to do is we're going to list all the queen variables first, from x1 all the way up to xn squared. And then we'll list the pawn variables from xn squared plus 1 all the way to x2n squared. And so this is a very simple conversion. You give me a pair ij for the queen, and I can tell you the corresponding index number. And so, did I write that down here? Yes. So that would be this line of code right here. If we have something at ij with ij between 1 and n, then the index position is I minus 1 times n plus j. So if you think about it, when I equals 1, j equals 1, we should be at index 1. When I equals 1, j equals 2, we should be at index 2. And then once we get all the way up to I equals 2, j equals 1, we should be at position n plus 1. So when I equals 1, we don't have any n's, we just have j ranging from 1 to n. Once I equals 2, now we'll be adding n to it, and this will just move us linearly down. For the pawns, all I have to do is add an n squared to this in front to just shift everything down. This code is also already on the web page, both as a Mathematica code and as a PDF file. Alright, so now we have our variables, in our mind as to where they're going to be. The first n squared are the queen locations, the next n squared are the pawn locations. I'm going to initialize my matrix A to be empty. I'm going to initialize my B vector to be empty. I could initialize my C vector to be empty at this point, but it's going to be so long before I work with C, I decided to just wait. You've got to be very careful that whenever you use things, you initialize them properly. If I had already run this program, I could have already had a matrix A floating in memory. And I want to just make sure everything is clear. So what I'm going to do now is I'm going to start adding the constraints. And so I'll spend a little bit of time going through this. I think it's worthwhile at least once in the class to go carefully through how you would write code to do something. So that's why, again, if you don't want to do this in Mathematica, if you want to do this in R, in C, in Python, in some other language that the CS people have created that I don't know about, absolutely fine. I want to talk a little bit about how you would convert the constraints to something that the computer would like. And so that's, if you're very comfortable with computer programming, that's how you should view what we're doing now. If you're not so comfortable with computer programming, concentrate now more on just how we actually do the coding. So what am I doing first? I goes from 1 to n, j goes from 1 to n. And what I'm going to do is for each square ij, I'm going to find all the positions on the board that could attack it. And so if there's a queen in any of those spots, I want to know if it's safe or not safe to put a pawn at location ij. So I'm trying to determine, is ij safe for a pawn, and I have to do this for all the different pairs. Alright, now number's going to go from 1 to n squared. Why? Well, we know that there are n squared locations for queens. And so for each location for a possible queen, I'm going to ask, does this location attack square ij? If it attacks ij, it's going to come into the constraint for the location ij. If it doesn't attack, I'm going to just put a 0 there. Okay? And so now we go through. B is equal to the mod of num n. So what this means is I take my number and I look at its remainder when I divide by n. And so the whole point of this is I want to convert from a number to a pair AB. That's going to be the location of the queen. Why am I doing this? If I give you a chessboard, can you tell if one queen is attacking another square? How do you tell? What are the ways a queen can attack a square? Okay, they can attack diagonally, laterally, and up and down. How do you tell if two things are in the same row? Yeah, you look at the row coordinate. So this is why I don't want to look at my queen as a number from 1 to n squared. I want to convert that number to a pair AB. I can easily tell if AB is in the same row as IJ. Just check, hey, is A the same as I? If yes, they're in the same row. If not, They're not in the same row. How do I tell if AB is in the same column as IJ? Yeah, is B equal to J? The diagonal isn't that bad. There's two diagonals. There's the diagonal with the +1 slope, there's the diagonal with the -1 slope. If A plus B equals I plus J, they're in the same diagonal. Or if I minus J equals A minus B, they're in the same diagonal. So it's really easy to check, does a queen at AB attack square IJ? And of course, when you're doing this, is it possible that the queen is actually at IJ?
Could you put palm?
So if you have a queen at IJ, can you put a pawn at IJ? No. So we will say that a queen at the square IJ is also attacking the square IJ. Which is very reasonable because the whole point is, can we safely put a pawn there? The reason we're not putting a pawn there is not because the queen is necessarily attacking the space, but because the queen is there. And you cannot have two chess pieces occupying the same space at the same time. Okay? So now, what I do over here is I now convert my number to a pair AB. And the nice thing about converting it to a pair AB, as I said, is it's very easy to check the conditions. One of the things that's a little bit annoying is when you do modular arithmetic. If you look at, if it's 10 o'clock now, what time is it in 5 hours?
3.
I'll try to provide coffee next time. All right, so everybody should agree that 10 plus 5 is 3. Right? What's 10 plus 4? 10 plus 3. 10 plus 2.
0.
Well, see, that's the thing. Is it 0 or is it 12? And so in our clocks, it's 12. In Mathematica, it's 0. Because they always use the minimal set of representation. They go from 0 to. And so over here, if I were to do this and try to convert to AB, I would actually be off by a little bit and my program would crash. Well, it wouldn't crash, it would just not give us the results that we want. And so what I have to do is I have to add this extra line. If B is equal to 0 after I do this remainder, then just change B to Bn. Because Mathematica is not using the mod function the right way. Another way I could do this is I could just redefine my own mod function. I could define Steve mod. And Steve mod is the same as regular mod unless you get 0, in which case you didn't get n. Okay? Was that a phone or what was that? Is that the sound of Munchkins? What was the cause thing?
I think so.
I think so. Alright, so Munchkins on Monday. Excellent, excellent. And my Skype is disabled, as is my phone, and my computer is on mute. Okay, so we have now the coordinates A and B of the square that we're investigating to see does it attack IJ. And now, this is how we do the constraint. If A equals I, or the two vertical lines means or, B equals J, or I minus J is A minus B, one diagonal, or I plus J equals A plus B, it's a -1, otherwise it's a 0. And so I made temp empty. Temp is going to be one of my rows of my matrix A. I've initialized it to empty, and I'm going to go through, and for the first n squared numbers, I'm going to put in a -1 if the queen attacks, and I'm going to put in a 0 if the queen does not attack. Now, I go num ij, this is the index location of my pawn location. I'll have to add n squared to it, but that's not a big deal. Now, and the num goes from 1 to n squared. I'm going to append things to temp. And what I'm going to say is that if my number that I'm at from 1 to n squared happens to be the same as the index of the pawn location I care about, I'm going to put in negative num queens, and otherwise I'm going to put in 0. And if you think about it, I've already put in n squared elements to temp, so this is now going to be the n squared plus 1, n squared plus 2, all the way up to the 2n squared elements. So I'm going to create a row now with 2n squared elements. The first n squared are going to correspond to the queen locations, the second n squared are going to correspond to things about the pawn. And my constraint, I'm now going to append something to B. I'm going to append negative num queens. And so if you think about what we're doing, let me just try to do this. We can make it much larger than that. Alright, so this should hopefully be visible. So what do we have? We have a sum over ij of xij, and we had a negative 1 in front of that. Okay, maybe this is too large. That's still readable. And now we had a minus num queens of pij, and that's greater than or equal to negative num queens. Oops, we somehow lost massive size. Okay, so this is the constraint I'm adding. Let's think about what this does. Imagine there were no queens. Oh, I'm sorry, this is not ij. We should really be calling this ab. And so this is summing over all ab that attack ij. ab attack ij. Okay. So we sum over all the pairs AB that attack ij. So imagine there were no queens that attacked the square ij. Then this sum would be 0, vanishes. And what do you know about pij? Is it constrained or unconstrained? It's going to be a 0, 1 variable. Do we have any constraint on pij? Could pij be 0? Yeah. Could it be 1? Yeah. So there's no constraint on pij. Later, we're going to maximize pij. We're going to maximize the number of pawns we can place. And so what this is telling us is, hey, if you have the opportunity to put a pawn here, you will. If you don't have an opportunity to put a pawn there, we now hope that it will say you can't. Imagine now that even one of the xab's were 1. If even one of them were 1, what would happen if this was 1? The left-hand side now would be larger in absolute value. It would be more negative than num queens. The left-hand side would be 2 negative if pij were 1. So as soon as one of the x's is 1, we have a problem. So what we saw is, that if no queen attacks, we will eventually have the pij equal 1. If even one queen attacks, we'll have the pij equal 0. This is exactly what we want to encode. It encodes it very nicely. How many of these constraints are we going to need? We're going to need n squared of them. 1 for each location on the board. Do you want to input all these constraints one at a time? No, and that's why you write the code. And so this is the code right here that's going to add all of those. And again, normally I do not have good habits like this. I normally don't put comments in my code. You really should. End of the I loop, end of the J loop, make it very easy to follow what's going on. Explain your logic as to why you're doing this so that if you're looking at this years later, you have a sense of what's going on. This is all we need to do to code the question of whether or not this square is safe. Okay? Anybody think of another constraint we need for this problem? So this will let us know whether or not a square is safe for a pawn to be placed. What else might I want to know?
We can't have more queens than the amount.
Yeah, you can't have more queens than the number of queens available. Right? No longer running such high-level code, so I can actually save a little power on the computer. Okay. Now, I wasn't sure if it was actually going to be able to run as board size as I wanted before class, so I really bumped up the system resources. All right, so we want to make sure we don't use more queens than we have available. So again, I'm going to initialize temp to be empty. I'm going to make another row for my matrix. For numbers from 1 to 2n squared, I'm going to basically be adding a 1 if number is less than or equal to n squared. So every time I'm at a queen location, I'm adding a 1. And then what I'm going to do for the b is I'm going to put the number of queens. And so what is this going to do? It's going to now give us, I'm sorry, I think I'm doing a 1. Yeah, I'm doing first as well. I'm doing, so I'm doing a sum of x a b, so that I have a minus sign now, is greater than or equal to num queens. That tells us that we have what?
At least 10 queens.
At least num queens queens. Well, if we want the other constraint, then all we have to do is replace everything with a negative. And that's what the next step does. And so now over here, notice we have exactly the same thing, except now we have a -1. And so now we've got a greater than equal to, because we have a negative sign, it's effectively the same as a less than or equal to. And so by putting those two in, we now guarantee that we have exactly num queen queens. Okay? Now the next thing is, oh, okay, now this is the fact that we want to have binary integer programming. And if Mathematica had the binary feature, which you would expect it has somewhere, I wasn't able to find it. I'm not convinced that it's not floating somewhere. It seems too useful of a thing not to have, but I couldn't easily find it in the code. It's not that bad. I'm just going to put in a constraint saying each variable is at most 1. And so that's what I think is going on for each of these. I basically have everything 0 except for that one correct space. Right, and that's it. That's all the constraints we need for the queen problem. Now we make our cost vector C. So initialize C to be empty for 1 to 2n squared. If num is greater than n squared, I put a -1, else I put 0. And the reason I'm doing this is I'm trying to maximize the number of queens. So how do I maximize the number of queens? So I want to maximize the sum of ij, pij. Are we allowed to maximize things? Does Mathematica give us maximization? No, so what do we have to do instead? We have to minimize the negative. So all we do is we change max to min. Well, actually, maybe we'll put the negative sign inside. And now when we do it like that, now we're fine. And so that's exactly what's going on here, is I'm putting a -1 in front of all the pawn variables. Alright, so now I just call my linear programming code, linear programming CA B vector automatic integers. And I'm going to save that into solution. I'll print out the solution. The next bit of stuff is just to format the answer so that it looks nice. If you think about what is solution, how many entries does solution have? So how many entries is solution going to have? 2n squared. So if I spit out solution, are you going to be happy seeing a string of 2n squared zeros and ones? No. Whenever you have something, you want to spend time formatting it, you want to make it nice. When I was in Princeton, I got a lot of funding for certain groups because we made our presentations in color, we had really nice documents. It's amazing what you can do if things look nice and professional. A lot of times as mathematicians, we don't really care, we look for content. I have been to talks in other departments with PowerPoint presentations that are almost like George Lucas films with movies going on and all these bells and whistles, and there's no content. And people are happy and they're having fun. I'm not. I want to see where's the beef, where's the interesting stuff. A lot of people, they want to be impressed. If you give them a string of zeros and ones, it's not that impressive. And also, does it really mean that much to you? Can you look at it and see what's going on? Not at first. How many of you have seen the movie The Matrix? So there's the scene when one of the operators says, I no longer see the code, I just see blonde, brunette, redhead. After a while, you start to visualize things. If you've worked in tech a lot or programming a lot, you start to see the tech almost compiled when you look at the source code. But when you're just starting out, it's much harder, and if you're doing any presentations, you want to display it nicely. So the next couple of lines is just to create a really nice board and to print things. I'm not going to go through the details of how you do that, but here's the module. And so I ran it in a bunch of different cases. So I first ran it for the 1x1 board. In a shocker, when you have one queen in the 1x1 board, there is no place to safely put a pawn. In the 2x2 case, there is also surprisingly no place to put a pawn. What about 3x3? Think it can be done for 3x3?
Yeah.
Nope. No pawns for the 3x3.
Oh.
Right? So a little bit of work, So now it's kind of interesting, because it's spitting out a certain configuration of the board. This is the maximum. There's lots of different ways of having no pawns. And so, one of the things that I find fascinating is why it's choosing this way as opposed to another way. If you were to change the order of the constraints, would you actually get a different null solution? And then for the cases where it's actually interesting and you can actually place pawns on the board, are the placements different, or are they all isomorphic under some kind of like rotation or flipping of the board? What about 4x4? Can we do it, yes or no? So here is one of the solutions. There is one way to do it on the 4x4 board. So it was 0 for 1, 0 for 2, 0 for 3, 1 for 4.
Wait, is num queens equal to our dimension?
Yes.
Okay.
I'm doing in place of putting n queens on an n by n board.
Okay.
And of course you can do the more general problem of what if you have more queens? What if you have fewer queens? And so this is one of the reasons why you want to set something up as a module. A module is the same as a procedural function. You want to be able to call it many times with different values. All right, what about the 5x5 board? What's the answer? Who remembers? 3. So we have the sequence 0, 0, 0, 1, 3. And here's one of the solutions. So the computer finds it. At this point, I've started adding the phrase timing in front. That tells me how long it takes. So it's taking me not even 1/10 of a second to run. But going from the 4x4 to the 5x5, and I actually told it here to print everything out. So there's the matrix. And actually it's almost all the matrix. So again, you don't want to be typing this by hand. And that's the matrix. Here's the B vector, here's the C vector. It went from about 0.1 seconds to about 0.4 seconds. So that's a significant increase in runtime. That's a factor of 4. A little bit more than a factor of 4. The next is the 6x6. Any guesses?
Like how long it will take?
Either how long it will take or how many. So we went from 0.01 seconds to 0.43 seconds. Any guess on runtime?
Sorry, that's 0.1, not 0.01, right?
Yeah, it was 0.09.
Oh, sorry, 0.09. Yes, we'll call it 0.1 seconds. Thank you. So any guess on the runtime?
Like a second?
2 seconds.
Okay, 1 to 2 seconds. And how many queens?
Wait, how many pawns?
Oh, so how many pawns? How many pawns?
7.
7. Alright, so this is now the 6x6 case. 5. So we're able to get 5 pawns.
5 seconds.
And it was 5 seconds. This was the 6x6. 7x7. What do you think?
7 pawns.
7 pawns. I mean, it kind of looks like 1, 3, 5, 7 seems reasonable. And you guess on the runtime?
Around a minute.
Around a minute, which would be how many seconds?
60.
About 60. So the number of pawns is 7. And the runtime is 138 seconds. It's about 2 minutes. So my fear is, how non-linear is this? How badly does the runtime go as we increase
Very
this?
not linear.
So very not linear.
That's a technical term.
It's a technical term, yes. If this was not being recorded, there are other technical terms. I've introduced my kids to the word shazafar, which is a bad word I use when I can't use the words I would like to use. So how long do you think it would take to do the 8x8, and what do you think the answer is?
I bet your computer had trouble doing it.
It actually solved it.
Okay.
So I think it's 9 pawns.
9 pawns.
Stick with that.
Okay.
20 minutes.
20 minutes.
Oh.
45 minutes. 46 minutes. So if you're looking at how much it's changing by, this is about a factor of 20. From 5 to 138, a factor of 20 would be about 100. So ballpark, this is actually maybe a factor of 23. 23 is not so unreasonable. So in terms of how long things are going, I have a rough sense How long would the next one take? Well, if it's around a factor of 20 again, this is taking an hour. I could probably do the next one if I let the computer run for a day. And so the number of pawns, though, is 11. Just barely fit it in. Are you surprised that it's 11? So when you only have a small amount of data, it can be very easy to be misled. How many of you have heard of the online encyclopedia of integer sequences? This is a great, great website. It's basically a collection of integers. It's searchable. You can search any string or substring of a sequence, and it will tell you all different things it knows. So somebody give me a famous sequence of integers.
1, 1, 2, 3, 5.
So if I only enter those, it's waiting.
Take a long time to search this website.
It should not take this long to load up. Definitely connected to the web because I'm uploading. Wow. Alright, there we go. So it found 279 results. What do you think I could do to have something more useful than 279 results? 13. If I add 13, I now go from 279 to 124. So let's do 21, 34, 55.
That sequence is pretty lame.
But at this point, I still have 23 different sequences. And so, if you start, not only does it give you the sequence, it gives you some names of it, it gives you different ways it occurs, it gives you links, it gives you generating functions, it gives you lots of properties. There's a huge wealth of information. It gives you a bunch of references, gives you links. It's an extremely useful site. It gives you a bunch of formulas for quantities related to them. The online encyclopedia is very nice. And now we eventually go on. Here's some code to work with it in different environments, Maple, Mathematica. Here's another sequence. The triangle read by rows.
That's just the Fibonacci.
So that looks like it's just the Fibonacci as well. So the question is, when is it going to be something really new? So next one would be what? 233? And so if we go to that, we're now down to 16. And so I'll just do one more, because I can do that pretty easily. So it'd be 377. Alright, so now at this point it's still 14. And then you want to start seeing how many of these are really fundamentally different. What sequence should I put in now?
Primes.
Yeah, put in this one, right? 0, 0, 0, 1, 3, 5, 7. I'm not going to put in the 11. And let's just see if we just do the 1, 3, 5, 7, how many things does it give us? Alright, so it gave us 11 different things. The next one here is 10. The next one here is 9, 8, 6. So this could be actually pretty bad. So now we'll put in 11. And we may have found a new sequence that's not in the encyclopedia. The maximum number of pawns that can be safely placed. No, one is found. And if you look at the name, the maximum number of unattacked squares with n queens on n by n board, answers for n greater than or equal to 17 only probable. So this gives you an idea of how far this problem has been pushed. Also gives me some confidence that the code is working well so far. So the online encyclopedia is a wonderful site. And then you can start to ask, well, what do we know about this sequence? Compare this to the Fibonacci's. What is the stark difference between this and the Fibonacci's?
Some of the information.
Basically, we have a table of values that someone has computed. And that's it. We have a link. We have a link to a table. I'll click on this. Statement of problem, history of the problem. So this isn't so bad. It gives you a little sense of the history of it. Some situations, some configurations. So that's a little bit useful. So if you get interested in it, there's at least some reading and some stuff you can do. But what you want to do is, the web is vast. There's a lot of information out there. You want to try to figure out a good way through it. So this was, a bit of a long lecture, but, I do think it's important to have, some basic programming skill. If you haven't seen stuff like this before, how you actually convert what we've done to something that's practical. And again, depending on the system you're using, you're going to have to do slightly different conversions. The conversions here are not so bad. It's pretty close to the canonical problem. You just have to keep adding things row by row, and you want to automate the code so that you loop through and you fill up the row. If you had to enter this by hand, it would just be very painful. So your homework is on the honor system to make sure that you can write a simple code to do something like the diet problem or something like this. I will give you something of level of difficulty equal to the diet problem on the exam for you to do at home. And so as long as you can do something like that in any environment, you will be fine. I just want you to have this as a skill. Okay, can you hit stop?